Shall we start?
Yes, yes.
Okay, I have a small update. I joined Amazon today.
Oh, yeah.
Alexa
Sorry
Labs. So anyway, we'll start with, so today's session is on convolutional neural networks and computer vision. So that is the first thing that comes to the mind when we talk about computer vision, convolutional neural networks in this deep learning era. So we'll right away jump to the contents. So we will draw some intuition from like classical image processing literature, what are convolutions and why they fit in beautifully to this area of image processing, computer vision, video processing. We'll see architecture of a typical convolutional neural network. We will see some common computer vision problems. We will go through a training loop, how we typically train a convolutional neural network, and we'll see some of the cool applications and where we are in terms of the current research. Definitely in the upcoming sessions, we'll see more of current research. So yeah, that are the contents to be covered today. Moving on. So before even we jump into convolution, let us just briefly recap. I hope you all know, but still we'll recap how images are represented, right? So when we talk about images, today we are living in a digital world. We talk about digital images, and in like if you have a signal processing background, you would know that digital means you have sampling and quantization. So an analog signal has gone through sampling and quantization. So what is sampling when it comes to images? So basically what you do is images are nothing but you are capturing a three-dimensional world and you are projecting the three-dimensional world into a two-dimensional plane. That is the plane of the image, right? Now sampling is you are basically dividing the entire plane of the image into grids, right? You are dividing the space into grids, discrete grids. So if I talk about this 8x8 grid, this is an 8x8 image where I have divided it into 8 rows and 8 columns. And as I guess Sumant was mentioning, images are nothing but represented as or loaded into memory in array data structures. So these are nothing but arrays, right? So if you use any typical package like NumPy, you will be loading it into basically array, or even PyTorch loads it into tensor. Tensor is nothing but an array. So grayscale image, it's a single channel image. Okay, before we go into that, we have one more thing in digital signals, that is quantization. So quantization is like how many bits we are using to represent a data, right? So this 1x1 grid, if we are using 8 bits per pixel, so this 1x1 grid is called a pixel. So when we say about 256 pixel image, that means we have 256 rows and 256 columns. We are dividing the two-dimensional space into 256 rows and 256 columns. So if we use 8 bits per pixel, our values can range from 0 to 2 raised to the power 8 minus 1. So minimum value is 0, minimum intensity value, maximum value is 255. So that is using 8-bit quantization. Grayscale image, it has got a single channel. So we have one channel and individual intensity values can vary from 0 to 255 if we use 8-bit quantization. Again, we have colored images. Colored images has 3 channels, red, green, and blue. And each pixel, again, this 1x1 grid, each pixel can be represented as 3 numbers. So 1 number each for the red, green, and blue channel. So you have 3x8 bits per pixel. So you are representing it using 24 bits. So that is about representing a digital image. Now coming to convolution. So on the left-hand side, you see I have a grayscale image, right? So this values, so this is a 256 plus 256 image, okay? Left side of it, you see shades of gray. All the intensity values is of 70. And on the right side, you see completely black portion, which has intensity value of 0. Now I take a small window, 8x8 window, and these are the values I have represented, okay, in this array. Now our objective is, so we see a vertical edge over here. So again, this is coming from classical image processing literature. I want to set up the motivation behind convolution. So we have a vertical edge, we can clearly see, right? So our objective is, can we do some simple mathematical operation to get an output image where wherever we are seeing this edge, basically I want to detect that edge where in the input image the edge is lying. So can we do some simple mathematical operation around it? So let's see what we can do. So let us say that we come up with this kernel, small 3x3 window. First column, all values are +1. Middle column, all values are 0. And the last column, all values are -1. And this is the original image that we spoke about in the previous slide, right? So let us place this kernel on this 3x3 portion. I am starting with row 0. Okay. And what I do is I take a place-wise, I multiply this individual components and then take sum. So 70 gets multiplied with +1, 70 gets multiplied with 0, this 70 gets multiplied with -1. Okay, this 70 gets multiplied with -1, again +1 into 70, 0 into 70, -1 into 70, +1 into 70. So we basically do this. This is the operation that we are doing. Final output is 0. I'm replacing this in the output image. I'm putting 0. What I do next, I shift the shaded region by 1 unit. So when Sumant was discussing about strides, this is what stride is. If we are shifting this window during convolution by 1 unit, the stride is of 1. If I shift it by 2 units, I get the window here, right? That is called stride of 2. So this stride is 1. I shift it by 1 unit. Do the same computation. I get the value 0. Again, I move it to the right by 1 unit, 1 pixel. I do the same computation. This time I get some value, 210, right? I keep on doing the same operation. Again, I get 210. Again, to the right, I move, get 0, get 0. Now I will start with the second row. The same operation I do, I get a value 0. So likewise, if we do this sliding window thing, and if we traverse the entire image from left to right and top to bottom, I'll get this as the output image. And very interesting thing we are seeing here, I have detected some high values where the edge is at the center of the image. I've detected some high values. So if I represent it as an image, I'll see dark regions everywhere and a very light, close to white color region at the center. So I've detected an edge. And this entire operation that we did till now is nothing but convolution. If you have a signal processing background, you might beg to differ, but this is what convolution is in image processing literature. Moving on, like this animation beautifully captures what all I discussed in the previous slides. So again, stride is 1. I'm moving this window by 1 unit, 1 row at a time, 1 column at a time, right? And this is how the output image is being generated. There are a couple of observations. The output image dimension is smaller than the original image. Okay, so if we have to preserve the output image dimensions, means if we have to get the output image dimension to be equal to the input image dimension, we can do so by using padding. Again, like if you remember the last session by Sumant, he spoke about padding, he spoke about strides, and that is what padding is used for. It is used to preserve the dimension. But for the sake of simplicity, this is how the output image dimensions are related to the input image dimensions. So if you have a n cross n original image dimension and the kernel width is f cross f, so this is a 3x3 window. So the output height will be equals to n minus f plus 1. So if you do the mathematics over here, simple computation, this is a 9x9. Original image is of 9x9. So n is 9. F is 3x3 filter. We are using 3x3 kernel. So f is 3. 9 minus 3 plus 1. So 6 plus 1, 7. You get an output image of dimension 7x7, which is again smaller than the original image. Original image was 9x9. So you can figure out, like if we use padding, how this expression gets modified. A simple term comes in for the padding, and that is pretty simple, and you can figure that out. I'm skipping that for the sake of simplicity over here. So this is what is convolution all about, right? Now, when we talk about convolutional neural network, in the last session, we went through a convolutional neural network basically coded in PyTorch, We saw convolution layers, max pooling layers, we flattened the output, and then we had a fully connected layer, which is nothing but the dense layer over here, right? So what is the difference between the convolution that we saw previously and the convolution when we talk about in the context of CNNs, convolutional neural networks? Well, they're not different. The operation is the same sliding window thing applies here, but only difference is, so this is a data-driven approach, right? You are basically training this network. And when it comes to training, what you are learning over here is the weights of the network. So I will use something. Yeah. So Professor, so Professor Anand was mentioning that neural network is nothing but a function, right? So your y equals to function of x and w, where w is the weights of the network and x is the input, right? So this is what Professor Anand had mentioned. And these weights are what are the learnable parameters. Okay, this is what is learned. So if you go a couple of steps back, I was convolving with a fixed kernel. This was a fixed kernel. I knew what I wanted to do. I wanted to detect the vertical edge. I came up with this kernel, which does this beautifully, right? But here, when we have lots and lots of images, basically coming up with fixed kernels may not cover the entire spectrum of features that we want to capture, right? So what we do is we set this up as an optimization problem, and basically you have lots and lots of training images. We pass it through the network. The network predicts something. We see how good or bad it is. So let's say we are working on a cats versus dogs classifier. We see if the network is predicting all cats as cats and all dogs as dogs, or it is doing like performing poorly on that. And based on that, we basically define a loss function, which quantifies how good or how bad our network is. And based on the loss function, we have subsequent steps, which I'll be covering next. And we basically provide feedback to the network to update its weights accordingly so that the loss is minimized in the subsequent iterations, right? So this is the iterative process. We do the training for multiple iterations, multiple epochs, and I will be covering them as we proceed. But again, coming to the point, the difference is these weights here when we talk about in the context of convolutional neural networks, these kernel weights are learned. They are the parameters of the network which are learned. But in image processing literature, when we spoke about that kernel, that was a fixed kernel. Okay. Moving on. Well, so these are like small blocks, small building blocks of a convolutional neural network. You have conv layer. If you remember in PyTorch implementation, he had used conv 2D layers. He had used max pooling, right? He had used linear layers for the dense. So linear, the class is called linear in PyTorch. So these are for the dense layers or the MLPs, right? Multi-layer perceptrons. So now we talk about this convolution layers. We will be covering each of this convolution max pooling operations and see what they are. Now, we discussed about convolution operation in one channel scenario, single channel scenario. So we had a window, 8x8 window, and the channel was 1. Now let's say we have an input volume, which is of size 32 plus 32 plus 3. For sake of simplicity, let's say this is an RGB image, right? So how the convolution operation will be, you will place this kernel, this is the convolution kernel, 5 plus 5 plus 3. You place this at this location, compute the output value, put the result here, shift it by 1 unit, again compute the output value, place it here, and likewise this output activation map will get created, this output feature map. These are called feature maps or activation maps, and I will be using those terms interchangeably as we proceed. Let's say we use a second. So this is again the computation. You have the input volume as 32. minus 5, n minus f plus 1. So we get an output map of 28 cross 28 cross 1. Right. Let's say we use a different kernel, a blue colored kernel, and that gives rise to another 28 cross 28 cross 1 activation map. We use one more kernel, the fourth one. So likewise, like if we use n number of convolution kernels, we get n number of channels in the output activation map. Right. So again, we'll go to this slide. If we say n1 channels in this, that means I have used n1 kernels. I have convolved this input image with n1 number of kernels. That's how I have got n1 channels, right? So here, if I say that there are 4 channels, that means I have convolved this input image with 4 kernels: red, blue, yellow, and green. Right. So this is what the convolution operation is exactly when we talk about convolutional neural networks. We use multiple kernels and we do a convolution using those multiple kernels. And finally, the number of kernels that we use is equal to the number of channels that we get in the output activation map. Now, conv layers are followed by nonlinear activations. So after this, we have some nonlinearity. Basically, if we don't use this nonlinearity, nonlinear activations, then like we are just doing some dot products. So that makes the entire, basically the entire network we can represent as a linear layer, and we want nonlinearities. Neural networks are high dimensional and nonlinear, right? So they are capable of learning nonlinear decision boundaries. So these activations are what induces the nonlinearity in neural networks, and we'll be talking about them in a few slides from now. Next, coming to pooling. So we saw max pooling. There is one more type of pooling which is rarely used, that is average pooling. So this is the scenario where like we take this 2x2 window, we compute the maximum value, we place it in the output. Then this is having a stride of 2 in this situation. We have moved the window by 2 units, take the max value here, we place it here. Again, we move it to the right by 2 units, take the max value here, we place it here. Likewise, we compute the output activation for max pooling. For average pooling, as the name suggests, we take the average of these 4 values and place it at the output window. Then again move. So this is using stride of 2. So we are moving by 2 windows to the right, 2 pixels to the right, or 2 windows to the right. We are putting this. So that is how stride, basically, if we take a stride of 2, you can see again the output activation map dimension is smaller than the input activation map dimension. Basically, it is dividing it by 2. And what pooling does is pooling. So when we spoke about convolution, basically these kernels are learning. Basically, they are learning weights which can act as feature extractors, right? One of these kernels might be figuring out vertical lines in the image, vertical edges in the image. One kernel might be figuring out horizontal lines in the image, horizontal edges. Something might be figuring out edges at some orientation, particular angle, right? So these kernels are learning them. What is pooling doing? Pooling is basically reducing your computation. It is downsampling the image, but at the same time, the objective is we are kind of capturing the dominant information, and we are not losing much information when we are downsampling. So pooling is basically fitting the objective better to your computational budget. So it is basically a downsampling operation. Okay. So we have till now we have discussed about convolution operation and max pooling. Next is the dense layer. So dense layer is nothing but multi-layer perceptron. What you do is, so if you have an input of 32 plus 32 plus 3, like last time when we saw with MNIST data set, we had 28 plus 28 plus 1, and we multiplied them to come up with a vector of 28 plus 28 plus 1 dimensional vector, right? So that was, I think, 784 or something. So here, if you have a 32 plus 32 plus 3 image, you basically flatten them out to a single dimensional, one-dimensional vector. So of you flatten them out to a vector of 3072 dimensions, right? 32 plus 32 plus 3. And then you multiply this by weight. some weight. So what is the dimension of this weight? If you want a 10-dimensional classifier output, like for CIFAR 10, this image dimension is from CIFAR 10 data set. So if you want, and CIFAR 10 consists of 10 classes. So if you want to classify it into 10 classes, you can have a weight of 10 cross 3072. If you multiply it with this vector, you get 10, a vector of 10 dimensionality 10, where each of this prediction corresponds to each of the classes. So this is what the fully connected layers are doing. And now we have this entire convolutional neural network. Okay, so we have discussed convolutional layers, we have discussed max pooling layers, we have discussed dense layers, we have discussed the flattening operation over here, right? This is the flattening operation that we are doing. Now, advantages of convolutional neural networks. So first is fewer weights. Let us discuss this. Let us see how it comes to how it fits into the idea of images so beautifully. So first thing is, let us say we have an image, right? And we have a vertical edge at the center. We have an image. We have a vertical edge towards the right, right? So if you can do the computation yourself, if we use the same kind of convolution as we discussed in the initial slides, the output image that we'll get. So for the first case, the output image will have the edge at the center. For the second case, we will get the edge towards the right. So basically what it is doing is it is somewhat maintaining the localization aspect, right? So wherever in the input image we have some feature, it is maintaining that in the output image as well. So this is the beauty of convolution operation. But whereas on the other hand, if you unroll it into a vector, you have lost all the spatial information. So in MLP, if you do it like, right, so if you have MNIST data set, which is a 28 cross 28 cross 1 image, grayscale image, so one dimensional. If you unroll it into a 784 dimensional vector, you have lost the spatial information. But this is the beauty of convolutional neural networks, whereas wherein this convolution operation basically preserves the spatial aspects. First, second advantage is so this is what, when I speak about features computed at translation invariant. So when the edge got shifted by right, my output in the output image also, the edge detected was shifted to the right. Second thing is fewer weights. Let us also see how this works. So let's say you have an MLP. So this will be, all these nodes will be connected. All the nodes in the input layer will be connected to the output layer. Right. So we spoke about, so this is the input layer. This is the output layer, right? Output layer has got a dimension of 3, input layer has got a dimension of 5. So to do some matrix multiplication and come up with an input of 3, my weight should be of the dimension 3 cross 5, right? Because X is of dimensionality 5, right? So if we do Y equals to WX, W times X, I get Y as a 3-dimensional output, right? So what is the dimensionality? How many parameters in W are we learning? We are learning 15 parameters, right? On the other hand, if we have to do it using convolutional neural networks, the same thing and let's say, so this is the 1D convolution. I'm not, for the sake of simplicity, I will talk about the 1D convolution. If we have a kernel of size 3, so previously we saw 3 cross 3 kernels. Here we are seeing size 3, one-dimensional case, right? So these 3 values and like kernels will have some values. So if we take the place-wise multiplication and do the summation, we get one value. We shift it towards the right now. We do the same operation, we get the second value. We shift it towards one more window towards right. We do the same operation, we get the third value. So how many like parameters are we learning in this case? We are learning just 3 parameters. So computationally, they are much more efficient than using fully connected layers. So these are a couple of advantages of convolutional neural networks and why they fit in beautifully to images and videos. So till now, we have seen convolution operations, we have seen max pooling, we have seen the dense layers, and we have discussed about why convolution fits into this domain of images and videos. We also spoke about activation functions. So each of these layers, each of this convolution layer is followed by an activation function, which induces some nonlinearity. In fact, each of these dense layers, the fully connected layers, are also followed by some activation functions, and they also induce nonlinearity. So what are the most common activation functions? They are sigmoid, tanh, ReLU, and leaky ReLU. For deep learning, when we use CNNs, or even if we use the linear layers, the dense layers, ReLU is the activation function of choice because, okay, I'll talk about that a few slides from now, why ReLU is beneficial. Basically, there is something, okay, I'll talk about that in a few slides from now when we talk about backpropagation. Till now, are the things clear? Like we can have some questions before moving forward. Yeah, so there is one question that says, by pooling, we are losing some information. So is pooling operation good thing or not? So yeah, definitely we are losing some information, but the objective, like when we use some function, like we are using the average function or the max pooling function, we are trying to preserve the most significant features. So average pooling is not used because it acts as a, basically it is weighing each of these features equally, whereas max pooling, what it does is, it is picking up the dominant feature and it is sending it to the next layer activation, right? So we are trying to minimize the data loss by good choice of activation, good choice of pooling functions. And any other questions? Okay, so we will. Now comes training CNNs. So right now, what we discussed is, we have discussed convolutions, we have discussed pooling, we have discussed dense layers, we have discussed why convolutions fits in better, and we have discussed a typical CNN architecture where like Lego blocks or building blocks, these layers are stacked up: convolution, some nonlinear activation, followed by a max pooling, followed by a convolution, and so forth, so on and so forth. And then you have a flatten layer, and you have finally you do some predictions in the output layer. There is one more question. Let me address that. Okay, yeah. So the question is about batch normalization. Maybe let me go through a few more slides now, and then I will be in a better position to explain batch normalization. I have not put it in the slide, but I will definitely do explain that. So now we come across, like, now we will cover training CNNs, right? So what we do is, so in this training loop, or like any data-driven approach, what we do is we go for a forward pass, then we propagate the gradients back, and which basically updates the weights, right? So in the forward pass, what we do, what all operations we discussed till now. So we have an input image, We do multiple convolutions, pooling, convolution pooling, then we finally flatten them out and make some output predictions. That is the forward pass. We are traversing through all neurons from first layer to the last layer. So that is the forward pass, right? And finally, we have a loss function that we discussed. And the loss function is used to quantify how good or how bad our network did in this pass. Like let's say we passed an image of a cat. If the network has predicted it as cat or with some probability, which is close to 1, or how bad it is doing, right? So the loss function will basically quantify that, how good or how bad our network is performing, right? Now comes the backward pass. So backward pass brings us to this important concept of back propagation, right? So what you do is, let's say you have a function y equals to fx. I'm doing some mathematics over here. Let's say we tweak the value x by some amount delta x, right? So how will y change? So that is nothing but del y by del x, right? So this where delta x is very small and it tends to 0. So this is nothing but basically this is nothing but we are taking the derivative. When we do it in high dimensional space, call it as gradients, right? What it signifies is, if we tweak our input parameter by some delta, how much is the output changing, right? So in our use case, what we want is, if we tweak our weights, these are the learnable parameters, our weights and biases. If we tweak them by a certain value, am I going to decrease the loss or not? So that is what we are interested in. We finally want like the training to progress in such a way that our loss goes down, our training loss goes down. When training loss goes down means our model is performing well on the training data, right? So that is our objective. Our objective is the loss should go down. So what we want to calculate is, if let's say a particular weight W, if you tweak it by small amount, is our loss going down, right? So we compute these gradients for each of this layer. We compute these gradients. Again, like you can go into details about how these are actually calculated, how chain rule is used to basically backpropagate the gradients. So that is what happens, and your backpropagation starts from your loss function. You compute the gradients with respect to the loss, and it propagates to the initial layers. So computation is made from last layer backward to the first layer, and the learnable parameters are updated. So stochastic gradient descent was discussed. I will give you some intuition about stochastic gradient descent, how it works. Okay. So let's say I have my loss represented on the y-axis. I have some parameter W, which is determining the loss, right? Y predicted is a function of input and W. Input is fixed, weights are what we are learning. And for the sake of simplicity, this does not apply to neural networks. Let's say what we do is, we basically, this is the ground truth, and we basically take the sum of squared error loss, and we divide it by, average it out. So basically sum of squared loss. So this is the equation of a parabola. So we have a convex looking function over here, right? This is where the loss is minimum. How we do the training? We start with some random initialization of weights. Okay, we start from here, let's say, and our objective is we should reach here. So what stochastic gradient is doing is, so at this portion, since this is a minima, delta loss upon delta W will be equals to 0. Elementary school level differential calculus. Now we see this equation, how the weights are updated. Okay, so W at iteration t plus 1 equals to WT minus alpha into del loss by del of W. What is alpha? Alpha is the learning rate. it determines how big a step we take, how big the update is. Okay. So here, if we take a small window, del W, this is del W. Okay. If we take a small window, what the losses happen? So initially we are here, we go on to this point. How the loss is changing? The loss is decreasing. So loss at W plus del W minus loss of W upon del W is a negative value because the loss is decreasing. If we take here LW, if we take here LW plus del W, so W gets changed from this point to here, we are moving. This loss is smaller than this loss. So at this point, this regime, this half, the left-hand side of this minima, our gradients are all negative, right? And on the right-hand side, if you do the same computation, this is del W, this is del loss of W plus del W, and this is your starting point, and this is loss at W. So this loss is higher than this loss. So your gradient is positive on the right-hand side. So it is negative here and positive here, right? Now you see the weight, see the update, how it is happening. Gradient is negative on the left-hand side. Let's say we start from here, okay? This is a negative value, and this negative and this negative will become positive. So ultimately we are ending up increasing the weight, right? So I was here, I do this update at W, so WT plus 1 will be greater than W. So what we are doing is we are moving towards this direction. And when we are moving towards this direction, initial weight was here, I have updated and I have moved somewhere here. You see that I am coming close to this minima, right? On the right-hand side, our gradient is positive, right? So this update, basically WT plus 1 will be lesser than WT because this is positive, right? So on the right-hand side, what we are doing is we are moving towards minima, right? So this is what stochastic gradient descent is. And this is what the optimizers are doing. Last time we saw Adam optimizer. Basically, there are like few drawbacks with stochastic gradient descent. The Adam optimizer helps overcome that, right? So there are different optimizers. I will just mention them and you guys can have a deeper look into that. But there are few drawbacks with each of them, and like we are trying, like the researchers are trying to build incrementally on top of each other to address some of these drawbacks and coming up with better optimizers. Right. So till training, so we have gone through, like we have seen the individual blocks, CNN convolutional blocks. We have seen max pooling. We have seen the dense layers. We have seen how training the forward pass and backward passes happen. Now there are some tuning parameters. We have some which are called as hyperparameters. And these hyperparameters basically influence the training dynamics, right? So first and very important of them is called learning rate. So the learning rate, again, as I was discussing, this alpha is the learning rate, and it determines how big or how small a step we are taking, like when we do the gradient descent, right? So when we have very high learning rate, basically the loss might shoot up. Okay, so I will try to show what might be the scenario happening in that case. Again, for the sake of simplicity, we'll go with the convex curve, but neural networks, the curves are very nonlinear and there are a lot of like local minima. This might be your global minima, but there are lots and lots of local minima and saddle points, right? So this is not an ideal curve for a neural network, but for the sake of simplicity, let us take this. Now, if your learning rate is very high, and you start from here, you might end up going like this in a zigzag pattern, and your loss might keep on increasing, right? So that is what is happening here. The loss is keeping on increasing when you are using a very high learning rate. When you use a low learning rate, your updates might be very small. So you are going towards the minima, but with very small baby steps. So it might require longer duration to train the network. So you see, this might ultimately converge to the local minima, but it might take a longer duration. When you have a high learning rate, what might happen is a decently high learning rate. You might come here. This is the local minima, and then you might start oscillating around the local minima, right? So with a high learning rate, what happens is you are making progress very quickly initially, but then since you are oscillating, you are not hitting the global minima, right? So the loss is not going down after a certain duration, and a good learning rate ensures that as you train it with for multiple epochs, a good learning rate to ensure that it is converging. Basically you are hitting the local minima. So that is how the training dynamics are influenced by proper choice of learning rate. Again, like, what are good choices? These are hyperparameters you have to experimentally determine. And with experience, you will get more intuition into how you can tweak the learning rate. Optimizers, again, there is stochastic gradient descent. I explained that stochastic gradient descent. There is RMS prop, and then ADAM is basically a combination of RMS prop and stochastic gradient descent. So there is something called a stochastic gradient descent with momentum. You can note them down. And since I have to, like, I just have a 1 hour session, I can't cover everything. But if you have any doubts, I will share my contact details and we can have a discussion regarding that. We can go into any depth. Next comes the activation function. We again discuss sigmoid, tanh, ReLU, right? So I will talk about briefly about why sigmoid functions are not used, right? So basically, we discussed about taking derivatives, right? Del loss upon del W, and we talked about the chain rule. So what chain rule does is, you have some gradients that is flowing in. Okay, I will make it flowing in from the right hand side to the left. And by chain rule, what you do is you multiply the incoming gradient with the local gradient. So what that does is, sorry, is there any question? Okay, so there are a couple of questions. Is CNN supervised or unsupervised algo? So CNNs can be learned both as unsupervised and supervised. So you have, when I talk about this classification network, I am using ground truth levels. So I am learning the weights using a supervised learning. When we talk about GANs, basically or autoencoders or variational autoencoders, that is the unsupervised scenario, but we don't have any ground truth level and we are trying to learn the distribution. Second question is, during backpropagation, we are updating only kernel with respect to matrix or dense layer with respect to matrix. Basically, we are updating everything. If we are using transfer learning, we can we can omit few layers, we can keep them fixed while we learn the classifier portion or a few layers of the convolution, depending on there are a number of parameters that basically determine that. I hope I answered your questions. So sigmoid layer, as you see, these are very flat regions, right? So the local gradients these regions will be 0. So basically what happens is this will kill gradients. So there is something called as, so local gradients will be 0. Your incoming gradient is multiplied with the local gradient. That is called as chain rule, right? So chain rule is like, if you have like del W by, if you have del L by del W1, and if you have del L by del W2 and del W2 by del W1, if you multiply this 2, you get this. So this is chain rule, right? So if, let's say this is your gradient that is flowing in, and this is your local gradient. If you use sigmoid and you are working in this regime where flat regions, the gradient here is 0, right? So it will kill the gradient. So the network effectively will not learn anything. We can again go into more details on this, right? So that is why ReLU is the choice of activation function. Sigmoid is rarely used for binary classification. In the final layer, we do use sigmoid sometimes. Yeah. Again, batch size also determines the training dynamics. What we do is we don't have infinite compute power, right? We have very limited compute power. So let's say we have a training data which has thousands of images. We can't load them at once into memory and do the forward pass, take a back propagation and update the weights. What we do is we divide the entire data set into small batches. Let's say we use a batch size of 8 or 16, depending on the compute we have, right? One more advantage of using a batch size is, like, we don't have to wait for the entire forward pass to happen on the entire data. Even with a batch size of 8, which is much smaller than the entire data set that we have, we are making some progress towards the local minima. We are doing the forward pass, we are computing the gradients, doing the backward pass, and updating the weights. So even with a smaller batch size, even with a smaller number of data set, which is a very small subset of the entire data set, we are making some progress. So that is how batch size helps. So batch influences, and I will share an article which beautifully describes how it happens. So you can go through that. Finally is the number of epochs. So basically, when you train this network, what you do typically is you keep on plotting the training versus validation curves, right? So what happens is initially you start, let's say you start with a high loss, high validation and training loss. And as you learn, your training loss decreases. Your validation loss also decreases, but you might encounter a scenario that after a certain point, your validation loss starts increasing. That means your neural network is trying to exactly fit to the training data. So when it is doing very good on the training data, the training loss is decreasing, but it is not generalizing well, right? So that is the problem of overfitting. So your validation loss increases. What you do at that point is you stop your training at this location, or you would have saved the checkpoint at this location. You use the model from that checkpoint, save checkpoint. Yeah. So finally, one more important concept is that of transfer learning. So in convolutional neural networks, again, like there are lots of standard data sets available. Like ImageNet has got thousands of images, lakhs of images, and 1,000 class data set. That is, like, you have 1,000 different classes, and you already have at your disposal networks that has been trained on this ImageNet data set. So you have model that was trained with some data one to perform some task one. So if it is ImageNet, you are doing a classification across 1,000 classes. And now let's say I just need a dog versus cats classifier. So what I do is I just replace the head. I make some minor modification in the network. I use the already learned knowledge from the previous task. I use it for this task. I copy the same model weights here. I replace the head. So basically, previously, if we have to do a classification across 1,000 classes, my output layer should have 1,000 nodes. Here, I am doing a binary classification. So I can just have 2 nodes, right? Cats versus dogs. And I can fine tune this network on my cats versus dogs data set, and I can get the predictions. So this is the idea of transfer learning. We have some question. Isn't it be good by going with low learning rate will play safe rather than high learning rate? So low learning rate. So what low learning rate means, you might end up like training for a long duration. So there are learning rate schedules. Initially, when you have high loss, you can go with a higher learning rate. But as you train for multiple epochs, you can slowly keep on decreasing. So that that would ideally mean that as you are trying to hit the global minima, you are decreasing the learning rate. So you can converge to the global minima much better. So these are approaches that are used to train. So there are learning rate schedules for that as well. So any question till now? I will go through some code, simple code, to cover all the concepts that we have learned till now before going on with the applications. Okay, one question was regarding, so please, yeah, one question was regarding batch normalization. Uh, so batch normalization, basically what you do is, let's say, I'll talk more about this. Let's say you have the loss contours as this, right? W1, and all points on this contour, like each of these contours will have the same loss, right? What happens with this kind of a setup is, basically, uh, along one dimension you are having, the slope is much steep. Along one dimension the slope is very shallow, right? So your update is much more along one dimension, your update is less along other dimensions. So what you do is you keep on following a zigzag path, right? So what batch normalization does is it is normalizing your activations, right? So you have this beautiful circular structure. I'm giving you the intuition. The mathematics behind it is you have some activation. What you do is you subtract it by the mean of the activation across that batch, and you divide it with the standard deviation. So you're normalizing it. And then what you do is, so this, let's say this is y hat. What you do is you set it up beautifully again, back to, you give the, so these are learnable parameters. You give the flexibility for this network to learn the mean and the standard deviation. So if this learns, if lambda, if this gamma is equals to this and this mu equals to b, it will learn the original distribution as a. So that flexibility is provided to the network, but at the same time, what you are doing is you are transforming the distribution. So batch normalization has got multiple advantages. What first advantage is, this is kind of a regularization. You are not letting the network learn a particular distribution, but you are changing the distribution here. So it acts as a kind of regularization in a funny way, of course, but so first is regularization. Second is it will allow you to choose higher learning rates. Why? Because if you choose higher learning rates here, you will end up taking this zigzag path. If you choose a higher learning rate here, you will move like this, right? Will converge much faster. So this is the reason why batch normalization is used. And I hope I have answered your question. Okay, I will take I will take all this. I will address all the questions later. Let me go through some code which I have written. I will cover the concepts there, and then we can come back to the questions. Right. So we were talking about cats versus dogs data set since morning, and I have the same thing at hand. So first few lines of code I want you to ignore. Basically, I am adding the code path to the system path so that I can access it. Deep learning frameworks, we already saw PyTorch being covered in the morning, and that helps me because I am going to use PyTorch for this, right? So we import the necessary modules. We import torch, we import torch.nn. So nn is basically the module with which we define, we write our own, we extend this nn class to basically write our neural networks implementation, right? So again, torch.optim, optim defines all this stochastic gradient descent, Adam, all these implementations are there in this package. From torch vision, we import transforms. Again, transforms are kind of, we are augmenting data. We'll see what all augmentation I have used. From torchvision.models, import VGG19. VGG19 is a very standard model. It used to be a state-of-the-art once. Now we have more advanced models. Again, I spoke about loss. So basically, we do convolution, max pooling, flattening, dense layers. And then finally, we use a loss function to say how good or how bad our model is performing. And one of those loss functions is cross entropy loss. So when we have the multi-class classification problem, very common loss function is cross entropy loss. Data loader, again, we saw in the morning session. So basically that is that creates a generator object. So if you are familiar with Python, you would know what a generator is. And so this custom data set I have implemented. So basically, if we call this custom data set, what I would get is I'll get one image and the associated label. So if it's a cat, I'll get an image of a cat and the associated label for that, right? Again, this is the architecture which we discussed multiple times today. Let's say we initialize the model and we make pre-trained equals to true. Pre-trained equals to true means it will download a model of VGG19, and the model weights will be the ones which it has learned. On what data set it has learned? It has learned on ImageNet data set. So if we see the components in this image, we have convolution layers followed by ReLU, convolution, ReLU, max pool. So all these building blocks that we have discussed, we can see over here. Kernel sizes 3x3, stride of 1x1, padding of 1x1, which would ensure that the input activation map and the output activation map are same in size. Then we have the adaptive average pooling. So this is also called global average pooling. So we have this average pool. We discussed about average pooling, and you can see what is global average pooling. Basically, this is replacing the flattening operation that we do. Then we have a classifier where linear layers correspond to the dense layers that we have used here. Okay, in PyTorch, that package is known as called linear. Right, dropout I have not discussed, but you can take a note, have a look at dropout. If any doubts, I'll share my contact details. We can have a discussion. But dropout is again one form of regularization. We don't want the network to perform very well on the training data, right? If it fits very well on the training data, it is fitting noise in the training data as well. So that might not help the network to generalize well to the test data on data which it has not seen. So for that, we use different regularization techniques. So that is it. Now, like I spoke about ImageNet 1000 class data set. So my output features has got like the last layer has got 1000 output nodes. So this will be 1000. So I'm doing 1000 class classification, right? Since it was trained on ImageNet. We spoke about transfer learning. Now we want this same network. I want to train on my cats versus dogs data set. So 2 class output. So how we are going to change is, see, I am using the same pre-trained network. I make it pre-trained equals to true means it will download the weights that it has learned on ImageNet, right? I am just replacing the last layer. I'm replacing it with a linear layer of 4096 input features, 4096, but the output features, I am making it as 2, right? For my cats and dogs, 2 classes. If I want to learn the initial layers, I can learn it, or if I can fine tune it basically. If I don't want it, I can make it false. So that will replicate the exact scenario. I am basically copying the weights that I have learned for ImageNet. I'm copying the weights directly, and I'm replacing the head over here with a different linear layer, which I'll be learning, right? If I initialize the model class, and if I print it now, see out features will be 2. Coming to the hyperparameters that I talked about, I'm using a learning rate of 0.01. I'm training it for 5 epochs, batch size 16, and device, I don't have, unfortunately, a GPU enabled device. This is running on my local PC, which does not have a GPU. So this is a CPU that says. We spoke about data augmentations, right? So what I'm doing is the input images might be of different shape and sizes. I'm first resizing it to 256 plus 256, randomly flipping it horizontally. There can be multiple more augmentations. I can like rotate it by some angle. So that is basically adding to the variation in the data, right? So that in a way prevents the network from overfitting. We are adding more and more data. We are trying to cover what all scenarios we can encounter when we do testing, right? So this augmentation is basically creating those possibilities, those combination of scenarios. Then we are converting it into tensor, and we are doing a normalization. basically subtracting it with the mean per channel mean and dividing it by the standard deviation. This is for the test transform. I'm not doing much over during the test transform because I just want to, I don't want to do a flip and random crop and all. I just want to test on the test data set as it is. I'm basically defining the optimizer here. I'm using stochastic gradient descent. Afternoon session, PyTorch session, we saw Adam optimizer, the stochastic gradient descent with some momentum. So SGD with momentum is one more thing that you can learn. We can cover this if time permits. And again, loss function, I'm defining as cross entropy loss. So this is the cats versus dogs data set. Have around 12,500 images for cats, an equal number of images for dogs. And I'm loading them onto memory. There are two labels, cats and dogs. Okay, and 1407 are the basically iterations, number of iterations that we'll have for the training data set, right? And each iteration, during each iteration means each forward pass, we will be using a batch size of 16. So we had a batch size of 16 and we will be having 1407 iterations, right? So this is the training loop, typical training loop. So we run it for number of epochs, and for each epoch, we are basically, one epoch means we are going through the entire data set. The entire data set, each of these images goes through forward pass. We do the back propagation, we update the weight. Here we are doing it in mini batches of size 16, right? So what we do, so again, like if it has to run on CPU, my model as well as my images should be moved to the CPU. If it has to run to the GPU, I have to move everything to GPU. So this two devices, what it exactly is doing. Otherwise, I will get error like something like torch.cuda.float tensor and weights are torch.float tensor. So those compatibility issues I'll get if one is on CPU and one is on GPU. So now this is the forward pass. We have the model, we pass the images to the model, we get some output, we compute the loss, and we call loss that dot backward, which basically computes the gradients of the loss with respect to each of the learnable parameters that we have set. Optimizer optim.step basically will update the weights. So optim.step is doing this. We had that expression. So optim.step will do this. Right. So after one epoch, we do the same thing with the validation data set. We run and check the accuracy of the validation data set. So the objective is, or if we check the loss, we should encounter a loss function like this. We should encounter a loss function like this. And if the training goes well, our validation loss should decrease while the training loss is also decreasing. But in case it deviates like this, we have to stop early. Since I don't have a CPU, I can't run it. It will take a lot of time, but I'll share this code and you can basically try out with different combinations of hyperparameters and you can check how the network performs. And finally, this is how you can save the network to disk. Yeah, so that's all till now, the training loop. And we have seen basically transfer learning. We have seen the building blocks in action over here, how the network is designed. You have conv layers, ReLU layers, and how we have seen the transforms that we apply. Basically, these are augmentations. We have seen optimizer, the loss function, and we have seen the training loop, right? So moving on to the applications, I'll quickly cover the applications. So we saw the image classification. We covered, we basically put a greater amount of time on image classification. There can be classification plus localization, where in the image you are determining what is in the image and where in the image it is there. Object detection is like multi-class classification plus localization. You have multiple objects. You are saying that within this blue bounding box, there is a dog. Within this small green bounding box, there is a duck. And there are two cats here. Instance segmentation is, so there are two types of segmentation, instance and semantic segmentation. Basically, segmentation is like you are coming up with masks along the boundaries of this image. So these again deals with multiple objects. right? So there are numerous applications. You have access control, so face detection, face recognition, and giving you access entry to a building. So that is access control. You have vision-based navigation. When we talk about self-driving cars or UAV navigation, vision-based navigation, that is what, like, you have cameras. It is saying, it is detecting objects, obstacles, and it is basically navigating based on what it is seeing. You have medical image analysis, like whether a CT scan has got some tumor or not, where in the image there is tumor, so that comes under medical image analysis. You have security and surveillance. You have some protected area, whether some person is venturing at that area or not, you detect that, trigger an alarm. There is safety applications. Nowadays buildings have like all the CCTV cameras. You detect whether the fire and all fire has been detected. You take the feed and say, like, okay, from this camera feed, we saw the network, the model basically says that, okay, the feed coming from this camera, there is some fire that has been detected. So yeah, so those are the numerous applications. Then there are some applications like image captioning. Based on the image, you are coming up with a description of the image. So image captioning is CNN plus LSTMs. So LSTM I did not cover. So basically you are coming up with some description of the image, and I have given all the links. If you want, if you are interested, you can go and check this out. Pretty cool applications. Then there is neural style transfer. You have a style image and you have a target image, and basically you are transferring the artistic style to the target image. A pretty cool application. Again, one more cool application is you are putting some textual description, and it is basically coming up with the animation. So they have a small YouTube video for that. You can check out this link. And so someone asked about, like, is CNN a supervised or an unsupervised learning? So these images have been determined in an basically created in an unsupervised way. These are machine generated images. They look so real. Seeing them, you can't say that whether it's a real human or not, but these people never existed in the earth. These are generated by something called as GANs, generative adversarial networks, and they are trained in an unsupervised way. And this comes from my alma mater. Few students of IIT Kharagpur came up with this self-driving car, and that has been deployed. You have a cool video on YouTube to check this out, and that has been deployed across some universities abroad. So yeah, so these are the applications. Frameworks and libraries: OpenCV, classical computer vision, image processing library. Then you have PyTorch, you have TensorFlow. You use NumPy operations a lot, and Pillow, Python imaging library, which is also called as Pillow, is one more. So these are the major frameworks and libraries that you use when it comes to computer vision. And few recommended readings. So I would recommend anyone venturing into this domain of computer vision to have a basic knowledge of how this traditional classical computer vision, classical image processing works. So that is my recommendation, because it helps to bridge the gap in approaches, the machine learning based approaches, and you draw intuitions from classical literature. That helps, I guess. So yeah, I'll take few questions. I see two of them already there. Regarding nonlinearity. What regarding nonlinearity do you, what is the conclusion that we get by introducing more activation functions in our network? So introducing activation functions is basically, it is introducing the nonlinearity. So what you might be ending up is, you might be ending up with, let's say, a feature space where this is the feature space, and you have one class of data which is like this. I'm trying to explain a very simple approach. I'm trying to explain it very simply, but yeah, you might come up with some data like this, and your decision boundary should be circle. So using activation functions, it is helping to come up with such decision boundaries. Otherwise, you might have a linear decision boundary where you will end up misclassifying many of the data points. So that is the use. Is there any difference between mini batch and batch size? So mini batch gradient descent, when we say, we talk about mini batches. So as I told, this cats versus dog data set has close to 12,500 images from each class. I used a batch size of 16, so that is the mini batch. So yeah, so in normal terms, we say batch size of 16, but that is a mini batch. When we do data augmentation, does the model learn on original data set appended with augmented data set? It trains with augmented data set. So every time we do some random augmentation and we train the model. When we do data augmentation, yeah. So I have answered this question, or does it trains on? So it trains with augmented data set on each epoch. So every time the data is randomly varying based on the augmentation that we use. Any other questions? How do you know if we are stuck at local minima? Okay, very good question actually. So your loss should decrease. Your training loss should decrease, and it should go to lower values. If it is not going, you can try out. So what you can try out is you can basically lower the learning rate. If it is still not updating, either you have hit a minima, that is a global minima, which should be a sufficiently low value, or if it is still not updating, you might be caught in a local minima. So, I mean, through experience, you would learn, but very hard to say like how to know whether we are stuck at a local minima. But then again, on the validation set performance, if you're stuck at a local minima on the training set, the validation set performance will be poor. If model accuracy is not good at early stopping, let's say only 30%, still can we use? No, I mean, again, like if training accuracy is just 30%, validation accuracy might not be good. So yeah, the network has not fully trained, so we can't really do early stopping there. We can try out other approaches like lowering the learning rate and see if it still updates the weights and if the accuracy shoots up. Any other question? Okay, I will share my mail ID in the chat, and you guys can shoot me an email.
Yeah.